Hello,
Great.
everyone. So I'm continue to share with you some basic troubleshooting skill today on the 40G and 100G transceiver. So as I highlight here, I'm gonna point it out what registers are there, some useful ones, and to set the CDR. And also set the CTLA, and last to set the transmitter and receiver squelch. Those 4 areas, usually we were not familiar with it in the lower speed, but from 40G and out, those are very useful, very important parameter to set due to the speed. So next week, like Priya said, I'm going to continue into part 3. Basically, I will cover sensitivity, and I set aside a time just for sensitivity because there's so many things to cover. And I don't want to overload you, and I pointed out some practical ones so you can find it useful. So first of all, I want to highlight some registers which are very useful for the 40G and 100G. The first one is the low power and high power, because some modules, it depends on the vendor, because the majority of the customer might want the module to start with the low power. So when you plug it in, nothing happens. So you can notice that the current is very low. So there is no optical power coming out, right? Very low. So by then, you should the first thing you should do is to look at A0 5D to change it into 04 hex. It should activate your high power. Second one is the 56. I talked about that last week about transmitter enable and disable. Third one was CDR. As I label 4321, 4321 transmitter and receiver. So each bit is for one entity. So to turn the CDR on and off. And the next 3 would be TX equalization, RX de-emphasis, and RX output amplitude. Those 3 are together, actually. We call it CTLA tuning. The last one, but not least, is the transmitter and receiver squelch, which not that many people pay attention, but I find it very useful for some customers. Okay, so I'm gonna go on. And again, I showed this last week. Basically, is where the CDR situated, because I'm gonna talk about CDR. So it's right here, and here's the equalization, just, by the way. And there are some, you can follow the block diagram to see what you can and cannot do, but some of the functions are covered by the MSA, some of them not. So it depends on the supplier. One highlight is that the CDR bandwidth is very important. So roughly the loop bandwidth is like a 10 megahertz to keep it locked and keep it jitter acceptable level. So CDR is basically people call it retimer also. And it is where the loss of lock and jitter generation occurs. And CDR, if the CDR is bypassed, which I will point it out, in some application, it needs to be bypassed. And you will be aware that running the bit rates, the specified bit rates of this transmitter is not supported because the clock is not locking. And then if you bypass the CDR, you get what that is. and I will show you some picture. And the second function of CDR bypass is to save the power, because CDR, usually the people use in this configuration like a 4 CDRs for modules. So you can imagine shut down a CDR, save a lot of power. Usually that's what the customer would request to do. So let me jump onto the CDR. Now, it shows you the CDR on and CDR off. So this, I need to spend a little time to explain what's happening. And right now, what it shows is that I run a 100G module, which you know is 4 times 25 G, and basically it's 25 gigabits per second, yeah. But I changed the file to run it at 10.3 gigabits per second, right? So most of the file can do that. But you know what happened is that when you run it and you have jitter like this, right? It's simple because the clock cannot be regenerated, right? Because you run it, the clock is supposed to lock on to the 25 G, but now the data is 10.3, right? You can imagine there's so much jitter. The clock try to reclock it, right? So there are humongous jitter here. But keep in mind, the center should be doable for the CDR to sample, right? So that's why it keeps locking, try to lock. So in order to get the one down here, which is the same signal, right? But if you can change the CDR to bypass mode, which is allowed in MSA, in register 62, A062, if you change to the 00, the clock will become very clean. Like this is 10.3 gigabits per second clock. So two things you need to check. One is to check if this function is supported, right? So there's an MSA register to check it. Secondly, and you need to change, you need to change the 62 hex register into 00, right? Immediately, you can see the loss of lock of the CDR. See, I just put it here this morning. I just realized that in order to explain, I better to use this statement here. If you see FF from A005, that means transmitter, receiver, CDR, loss of lock are all set. It shall be all set if you change the data rate into 10.3 gigs. Okay, so if it's not set, there's something wrong. So data like that, it should be all set. So the loss of lock should be all set. So, but if you bypass the CDR, it becomes like this. It becomes very useful. I usually use the 100G channel to generate 10.3 signal. So I don't have to have a 10.3 generator. Okay, so that serves the purpose. The next one I'm going to talk about is I call it CTLE, which some of you already know that because the data rate involved and is pretty long on the host board, right? For instance, that's the host file here is pretty long. It defined by this spec here, right? So supposed to, the budget is 7.3 and so on and so forth from TP1 and TP4. And what that CDLE doing is that they try to emphasize, try to do an equalization on the transmitter side or the emphasis on the receiver side, right? Basically, this is the reason I put it up here. And when you do it in the lab, that's how the transceiver people do it in the lab. So they have this HCM, which is called host compliance board, to plug into one of the slots. So you can imagine the slots is all here. They have a worst case slot and they have a best case slot in terms of the length of the trace. So they need to do all of them to verify it works. So that's how they do it anyway. So you can see some CTLE function here, and like the CTLE is changed on port 1 and port 16. That happens to be the minimum and maximum channel of this picture.
Eric, we have a question on CTLE in the Q&A.
Let's
see if we can answer before going on. Just what does CTLE? What is CTLE? Like, what does it stand for?
It's continuous time linearization equalization, right? So it's just like the word. It doesn't mean too much. It's a continuous time linear equalization. So basically, you change the shape, the rise time and fall time. In practical term, you change the rise time or the fall time in order to generate this MSA compliance trace, response. Thank you, Priya. And I don't remember where to click the question. So let me go on. So now, that's what I try to talk to you about. I don't try to talk to you about this because we, in fact, a customer, very seldom they go into this area. It should be done a long time before the product is released. What I'm trying to tell you is that there's a way to verify that, which is this. So you can see I highlighted here, right? Receiver amplitude and transmitter equalization. You can change that at this location, right? So if you change your 00, 11, 22, 33, you can see it's a 10 dB step. The range is 10 dB from here all the way to here, right? Here I don't change it. I map a 00, which happens to be the output amplitude 200 to 400, right? So I run, basically, I change the parameter and run the PRBS test in the switch itself. So I gather a whole bunch of points here, right? You can see the zero count is all 00 because this module is good. I'm going to show you one, the module is bad. So you know exactly what I try to tell you. So here is some parameter. You can get this presentation afterward and then try to digest it. If you don't understand, send me an email and I will reply to you. And here is another bad transceiver, which I've done almost practically the same thing at different level, at different transmitter equalization value. And then I capture the error coming out, right? Because at each point, at each setting, each line here, I run the test, run the test, run the test, right? So I count the error, right? So I get a whole bunch of error and I plot that out. The way I'm going to talk about bit error rate next week and in depth, and so you should understand it better. But here is a simple formula to manually calculate the bit error rates, right? For instance, if you have 7 error, the bit rate itself is 10.3 gigabits per second, right? And I run it for 30 seconds, for instance, right? Exactly this formula will tell you. Then I end up with 2.26 e to the minus 11. So that's how I figure out this axis here. So I plug it after I calculate the bit error rate from this axis and I plug it out. So it's very interesting.
Eric, I think you.
Output 2.
Yeah.
Yeah.
I think we lost connectivity for a minute. I couldn't hear you. Yeah, you can go on.
Okay, I'm fine now. Okay, so two curve here, right? So you can see the CDLE tuning also depends on the output amplitude, right? So output amplitude 300 to 600 millivolts per peak to peak, and here is 600 to 1,200 millivolts peak to peak, right? Two different curves. So I plotted out. Now I'm going to point it out. It's very interesting. That happens to all CDLE tunings. You can see here it's error free, right? Let me go back to the other one, the good one. See here, it should be all 0.3. Doesn't matter what the range is. If the tuning has 0 to 10 dB range, you should exercise this tuning range, and it shall be 0. If it's not 0, the transceiver vendor has a problem. Okay, so this one they have problem. So which means the area is very small. Any variation is going to give them error, right? You can see here. So this picture is not acceptable. You need to have this, okay? So one way to verify exactly like I do, use the MSA register to set it to run the whatever PRBS test you have accumulated and convert it into bit error rate and plug that out and see if you have a straight line on the floor. If you don't, you got a problem. Okay, so that's why I try to point out. And the last parameter I'm sorry, I'm a little bit over 20 minutes. The last parameter I want to point out is this so-called squelch. Most of you would know in the old days, receiver LOS tracks input power, average power. But when we move to high speed, like a 40 gigabits per second up, the CDR does not track average power anymore for LOS. They track receive amplitude, peak to peak, right? AC, we call it AC. So what happens if there is no data coming in, right? For instance, if the transmitter data is shut off, but the average power remain the same, optical power remain the same. So if that happens, you would have a situation called chatter, right? You can see on this picture all the dot here. Basically, those are the chatters because the transmitter is at a unknown state. The bias is so close to the threshold here, and any variation due to temperature, due to voltage difference, would generate random noise like this. And down the link, the receiver would interpret it as signal, right? That is not acceptable on some of the system. They want a clean line, right? I don't want any noise. Some customer come to us. I want a straight line. So if that happens, there is a way to fix it, right? So you go to register, right? Page 3, and FO, right? You set it accordingly on just like this table. I just map it out for you. They have a receiver squelch or transmitter squelch. You pick what you want. You set this register like this, and it shall give you the desired results, right? So, but some customer, they want chatter because they want the link always to be on. It doesn't matter. So some of them don't. So this is one parameter you can play with on the transceiver. Yeah. So what I'm trying to tell you is that there are knobs in the MSA table you can play, you can use to do your design, to have the maximum flexibility. And that's the end of my talk. And I will talk to you about some sensitivity measurement next week. And let me see if there are any questions. Let me see, question. Oh, there's some question, okay. So, okay, I'll answer the first one. The first question is CTLE stands for and continuous time linear equalization. And the second one is CDLE an emphasis internal high power filter in the chip, analog or digital? They are all digital, right? So, but in a way, they are not DSP, right? They are not processed by the DSP so-called 400G engine. So there are, if you are interested in CDLE, there are lots of material to cover this. There are different tabs. There are different areas. You see, usually I don't want to go into this because this is like done by the transceiver designer, right? So you don't try to tune it in a way that to change its characteristic. You just want to go through the MSA table, right? So yeah. The second one is that the value of the register which need to be changed to avoid chatter, right? I already pointed out, right? And can this be done by anyone or just the manufacturer? No, as long as there's MSA, as long as they say their module is compliant to this MSA, they shall supply you with the tool. Let me go back one more time here, right? So here is what you should enter: OF, FO, FF, or OO. There are 4 scenarios. You can exercise to see it. So yeah. All right. So that's the end of my talk, and thank you for listening. Hopefully, I talk to you next week.